Variations on changing the dielectric. Here we determine the equivalent resistance when the region between plates has been filled in some fashion with two different dielectrics. Consider figure 1, a capacitor with a vacuum between its plates, so the dielectric constant is 1, has plate area A and plate separation D. Those values used in the equation for capacitance give us a capacitor having an original capacitance of C naught. So far, so good. We then add two dielectrics in between the plates. The top half of the region, i.e. 1/2 of the area, has a dielectric of K equals 2, while the bottom half, the other half of the area, has a dielectric of K equals 4. The plate separation remains at D. So that's what we're showing here. Here's the original case, and then we're going to put in two different dielectrics, one in the top half and one in the bottom half. In terms of C naught, determine the capacitance of the kappa equals 2 portion. The capacitance is the dielectric constant times epsilon naught times the area divided by D. Now, what has happened here? The dielectric constant used to be 1, but now it's 2. Epsilon naught is, of course, the same. The area used to be A, but now it's 1/2 of A. And D is the same as it was before. The capacitance of just this top half, there's a 2 and a 1/2, it's still C naught. That top half has the same capacitance as the whole capacitor did before we did anything. All right? What happens with the bottom half? Again, let's write the equation out. Epsilon naught is a constant, so that hasn't changed. D hasn't changed. A is 1/2 of what it was before. And in the bottom half, the dielectric constant has changed from 1 to 4. So just the bottom by itself has twice the capacitance that the whole original capacitor had. You can think of these two regions as being two capacitors. And would those capacitors, look at the picture, would they be in series or would they be in parallel? They're in parallel with each other. So what's the equivalent capacitance? The equivalent capacitance of capacitors in parallel is just add them up. In this fashion, when we put a dielectric constant of K equals 2 in the top half and a dielectric constant of K equals 4 in the bottom half, the total capacitance of the new thing is going to be 3 times what it was. Refer now to figure 2. We start again with a vacuum between the plates. Plate area A, plate separation D. This results in a capacitor with capacitance of C naught, just like before. When we add dielectrics this time, the left half gets a dielectric of K equals 3, and the right half gets a dielectric of K equals 6. So you can see here in figure 2, in the upper right portion, the effective thickness of each of these is now 1/2 D. 1/2 of D for K equals 3 and 1/2 of D for K equals 6. In terms of C naught, determine the capacitance of the K equals 3 portion. Once again, the equation is K, or kappa, it's actually kappa, times epsilon naught times A divided by D. The dielectric constant is now 3. It was 1. Epsilon naught hasn't changed. The plate area is the same, but the plate separation is 1/2 of what it was. What does that give you? Doesn't that give you 6? 3 divided by 1/2. How about the other portion? Again, K epsilon naught A divided by D. The dielectric constant is now 6. Epsilon naught is the same as it was. The area is the same as it was, but D has gone to 1/2 of what it was. So that's going to be 12. We can think of these as two capacitors here, one there and one there. And hopefully you can see that those are in series with each other, one right after the other. And therefore, if we're going to determine the equivalent capacitance, whenever we do capacitors in series, we need to use what I call the 1 over equation. So we're going to go 1 over 6 plus 1 over 12, and then we're going to take the reciprocal of that. 1 over 6 plus 1 over 12, and then we got to go 1 over that. When we do that in our head, this would be 2 12s, so that's 4. 4 times the original capacitance. The new capacitance of this thing is going to be 4 times what the original one was.